We are in section A3 of Aerospace 305W with Tomar as our TA, and we conducted an experiment on March 11, 2024 to figure out how to develop a model for lift and drag for a thin four-bladed cambered air fan. My name is Jacob Spirages.
I'm Joe Messner.
I'm Brendan Quinones.
I'm Kiara Cornell.
I'm Rachel Shiflett.
And I'm Pierce Conner. So our objective for this experiment was to design and perform an experiment to determine the coefficient of lift and the coefficient of drag of two thin cambered wings to predict the performance of a given four-blade wind tunnel fan. In the top, we have a diagram of where the blade will actually be operating. And then down below, we are given some conditions and some operating conditions and measurements of the fan itself. And for the design considerations, when designing our experiment, we first had to choose which 3D wings we were going to test. Based on measurements, the camber of the fan blade appeared to be in between wing 2 and wing 3. So we chose wing 2 because it was below the camber of the fan blade, and wing 3 because it was above the camber of the fan blade. So we predicted that the fan blade performance should be somewhere in between the performance of wing 2 and wing 3. And then we had to decide how many experiments to run, and we determined that we should run one with wing 2, one with wing 3, and one experiment to determine the tear forces of the balance.
For the tear forces, we accounted this from the balance alone by taking data from a run without a wing attached. These tear forces account for any of the forces in the wind tunnel that contribute to lift and drag that do not include our wing. During this experiment, we are going to establish the limitations of a max angle of attack between -20 and 20 degrees, maximum velocity of 100 feet per second, maximum force of 50 pounds. So for our equations, we have our known values, which are going to be S, which is the wing area. We have the chord, and then accounting for air as our medium, we're going to use the density, which is rho, and our dynamic viscosity. For here we have the coefficient of drag, which is the drag force divided by the dynamic pressure times the wing area. Our coefficient of lift is going to be the lift divided by the dynamic pressure times the wing area. And our Reynolds number was valued at the density times the velocity times the chord divided by the dynamic viscosity. And our dynamic pressure is given as 1/2 times the density times the velocity squared.
Because we chose to model the fan blade using wings 2 and wing 3, we have the information about the measurements given in this table. So the camber for wing 2 was 2.8%, while the camber for wing 3 was 5.2%. We predicted that the fan camber would fall somewhere between 5.2 and 2.8%. And in terms of angle of attack, we're limited between -20 and +20 degrees. The angle, or the coefficient of lift graph for angles of attack between -10 and +10 degrees is approximately linear. So we chose a couple of points between, or a couple of angles of attack between -10 and +10 to represent this linear portion of the graph. And greater angles of attack produce non-linear coefficient of lift values. So we chose more points in this range to account for the non-linear portion. So in terms of Reynolds number, we chose to use a velocity, We chose a Reynolds number based on the average velocity in the wind tunnel. So we initially wanted to use the velocity of the tip. However, after calculation, it was greater than the maximum velocity in the wind tunnel, which is 100 feet per second. So we took the average between the velocity of the root and velocity of the tip and used that to calculate for Reynolds number. Our Reynolds number came out to be about 291,000. So in terms of our experiments, we chose to do 3 experiments. We used a balance as shown in the pictures to calculate or to measure the near and far lift and drag forces as well as the pitch of the airfoil. Experiment 1 focused on gathering data for wing 2. Experiment 2 focused on gathering data for wing 3, and experiment 3 focused on getting tear data.
When considering which published data to choose from, we wanted a wing that was similar to the wings that we tested in this experiment, as well as a similar environment in a low speed wind tunnel. Our aspect ratios for the 2 wings were about 2, while the semi-span aspect ratio for the published data wing was about 3. The camber for the wing in the published data was about 4%, while our 2 wings had camber of about 2.8 and 5.2%. These are the lift force curves gathered from our data. The tear is displayed on the graph without being subtracted from the lift force. The curves are linear in the middle on either sides of the angles of attacks of 0, -5, 5, but are curves at the end towards the angles of attack of 20 and -20, indicating stall. Similarly, these are the drag force curves with the tear displayed. Wing 3 has a higher drag force than wing 2, and the angle of attack is highest at 20 degrees, but wing 2 has a higher angle of attack at -20 degrees.
This graph plots coefficient of lift as a function of angle of attack alpha with the tear data subtracted. And similar to the lift force graph, we can see that wing number 3, which is more cambered than wing number 2, produces a higher coefficient of lift, which caps at about 1.25-ish at 19 degrees. But as we can see, it starts to level off, which indicates an approaching stall. We can also see that both wing data adhere closely to the published data, which proves to us that our data was gathered in an accurate manner. Now for the drag coefficient as a function of angle of attack, it is also similar to the drag force one, as the tear did not change the forces too considerably, but it was taken into account in this graph. And we can see again that wing number 3 produces more drag with a positive angle of attack and less drag than the less cambered wing number 2 at a negative angle of attack. And again, both wing data adhere closely to the published data, which proves that we collected it in an accurate way.
So we formulated a prediction for the performance of the fan blade by taking the midpoint between the CLs and CDs of both wings. So we plotted this versus compared to data found for the actual fan in Lab 5. And as you can see, the CL prediction matches very closely with the actual data, showing that our prediction of a midpoint is fairly accurate. Again, this is a plot of CD prediction versus the actual data gathered in Lab 5, and again, a very close match, showing that our midpoint prediction is a valid model for the fan blade performance. So, in conclusions, the data collected for CL and CD of the 2 wings matched the trend shown in published data, showing that we were processing our lift and drag data correctly, meaning that the data that we're taking the midpoint of to perform our model is itself accurate. And then the average CL of our prediction was 0.25, and the average CL of the fan from the performance data was 0.31, so again, close. And then the average CD predicted from our model was 0.2, and the average CD of the fan was 0.17, so again, very close. So this basically, all this really means is that the midpoint prediction of the fan blade performance that we made matched well with the actual data, showing that as a valid model. And then here are references for our published data. Thank you.